G'day, Richard Marr here again from Mars Classes. This episode we're going to have a look at the concept of work being done on an object when you move it in a gravitational field. Now, when we look at work, we're looking at a force moving an object through a distance. The concept of work, or the terminology work, is not probably the same as you would recognise in normal English. So let's have a look at the derivation of the term. Ancient Greek, the word for work was ergon, and the ancient Greek word for in is en. So in ancient Greek, they had a word when they combined them to mean if something had work in it, the energia or something along those lines. Now, throughout changes throughout history from French and Latin, in the mid-16th century in English, we came up with the term energy to mean that something had the ability to do work, or had work in it, or it could cause changes. So that's the derivation of it. So in essence, energy and work are pretty much the same. So whenever work is done, energy is involved. And that's probably the best definition we can get for it. So what that means is that energy and work are almost equivalent. We know, as I think I've said previously, that we can calculate the quantity of work done by multiplying the magnitude of the force times the displacement in the direction that the force acts. So if we lift an object in the Earth's gravitational field, we're doing work on that object because we're overcoming the weight force of that object when we lift it. Now, we can calculate the weight force of that object, and I'll explain this in another episode, by multiplying the mass of the object times the strength of the Earth's gravitational field at that point, or the acceleration due to gravity at that point. So we can say the weight of an object is mg. So if we're doing work by overcoming that force, and we've said that work is force times displacement, instead of just the term force, we can put weight force times displacement. So the work done by lifting will be the weight force times the displacement. And we've said that the weight force is the mass times acceleration due to gravity at that point in the Earth's gravitational field. So we can then write it as mass times acceleration due to gravity times the displacement. Now if we're lifting it, the displacement is going to be the height that we lifted. So the work done by lifting is mgh. Now you've probably already recognised mgh from your lower school work, and that's equivalent to potential energy. So if we're doing work by lifting something, the thing will be gaining potential energy equivalent to its mass times the gravitational field strength times the height that you lifted. So let's have a look at the units here. Now, work and energy we're saying are equivalent. So the units for work are in joules, and the units for potential energy are also in joules. So let's have a look at the mgh, because they should then come, the units should all equate. So the mass is in kilograms, acceleration due to gravity is meters per second, and the height is in meters. So let's simplify that expression for mgh, or the units for mgh, and we can get that it's kilogram meter squared second per second. And we can simplify that even further by saying kilograms times meters per second all squared. And when we look at those units, we see that kilogram is the unit for mass, and meters per second is the unit for velocity. So really that's like an mv squared. So we can see that if they are the units, kilogram, meters per second all squared are the units which are equivalent to joules, we can see that actually kinetic energy, which is half mv squared, will also have the units of joules. So what that's telling us is back the old law of conservation of energy, which you've studied in previous years, and that is that you can't create energy from nothing, you can't destroy energy so no energy remains. All that you can actually do to energy is you can transfer it from one place to another, or you can transform it from one form to another. So it can transform from potential energy to kinetic energy, for example. So let's have a look at a situation where kinetic and potential energy are being interchanged. This law of conservation of energy means that the total amount of energy in a system will always remain the same. So if we're looking at the sum of kinetic and potential at one point in a system, it'll be the same as at another point. So let's have a look at a satellite orbiting the Earth. This particular satellite, you'll notice that I've got it in an elliptical orbit where it's a bit closer at one point of its orbit and a bit further away at another point of its orbit. This is an elliptical orbit where the centre of mass of the Earth is one of the foci of the ellipse. The closest point is called the perigee, and I'm saying this one is 250 above the Earth's surface. And the apogee, the altitude, is 500 kilometres above the Earth's surface. We know that the radius of the Earth, or the mean radius of the Earth, is 6,375 kilometres. So if we wanted to find out not the altitude above the surface but the height above the Earth's centre, we'd add the mean Earth radius to the altitude, and therefore at the perigee we've got 6625 kilometres and the apogee is 6875 kilometres. I'm going to say now that the satellite's mass is 1,000 kilograms, just so we can do some calculations with it. Now if that's the case, and I'm also going to give a velocity at the perigee of 7,828 metres per second. Now, at the perigee, we will be able to work out its kinetic energy. And we know that at all points of the satellite's orbit, the sum of its potential and kinetic energies will be constant value. So we can work out the kinetic energy at the perigee. If we were asked to determine the kinetic energy at the apogee, or the velocity at the apogee, how would we do it? Now, a lot of you would probably say, oh, well, we'll do mgh at the perigee, add it to the half mv squared at the perigee, do the mgh at the apogee, and then the only unknown will be the velocity at the apogee. We can work out the velocity. There's a bit of a problem with that. The gravitational field strength at 250 kilometres above the Earth's surface will not be 9.8. So when we're doing mgh, we don't know what the gravitational field strength is at that distance above the centre of the Earth. So we have to do a few other things. Now we do know that the h above the centre of the Earth is the radius of the orbit. And we do know that the mg will be the force of attraction, or the gravitational force of attraction between the mass of the satellite and the mass of the Earth. So if that's the case, to work at that gravitational force of attraction, we can use the equation g m1 m2 on r squared, where m1 is the mass of the Earth and m2 is the mass of the satellite, and the r is the radius of the orbit, or the distance that it is away from the centre of the Earth. Now we can simplify that down and get just g m Earth mass satellite on radius of orbit. So what we've done is we've said the potential energy at that particular height is that value there. Now we can go ahead and calculate the total energy at the perigee. That's the sum of the kinetic and potential. We can do the same thing to work out the potential energy at the apogee. The difference between that and the original total energy will give us what the kinetic energy is, and then we can work backwards to determine what the velocity is. Now I'm just going to give you a couple of seconds. If you pause the video now, and then I'll come back with the answer. Okay, if you've done your calculations, you should have found that to be the velocity at the apogee. Okay, look, I think that's enough for today. I'll see you guys next time.